this lesson we consider the so-called Superdense Coding protocol. It is one of the two protocols of quantum information transfer that are presented in our course. The second one, which is the protocol of quantum teleportation, will be considered later. Both protocols include two participants being in different locations and the task of information transfer between them. For example, the members could be in different cities. By tradition, these participants are called Alice and Bob. The notion of the information channel or the channel of communication is also being often used. We will define it properly when we consider the error correction. We now only know that the classical information channel allows one to transfer classical bits of information, while the quantum one allows transferring qubits. According to many protocols of quantum information transfer, like superdense coding and quantum teleportation, both Alice and Bob have a qubit, and this qubit is prepared in the Bell state beta 00 at the beginning. So, if Alice's qubit appears to be in the state 0 after the measurement, then Bob's qubit will also be in the state 0 after the measurement. If the measurement of Alice's qubit shows 1, then Bob's qubit will be also in the state 1 after the measurement. Sometimes the presence of a Bell state between Alice's and Bob's qubit referred to as the preliminary contact between Alice and Bob. The scheme for the generation of the Bell state beta 00 is presented on the slide. Two qubits in the state 0 are sent at the scheme's input. Then the Hadamard transform is applied to the first qubit. This results in the first qubit being in the superposition of states 0 and 1. Thus, after the Hadamard transform, the general state of qubits is a superposition of states 0, 0 and 1, 0. After that, the CX gate is applied to the superposition, and the second superposition term changes to a states 0 or to a states 1, 1. As a result, the Bell state beta 00 is obtained. Actually, this scheme is not being used in practice for the Bell state generation. It's much more easier to obtain the Bell states from the physical sources of them. We'll talk about these certain physical processes in the next lessons of our course. However, the scheme for the generation of the Bell state is of importance because the reverse scheme you see is being used for the measurement of the Bell states. In fact, such measurements allow one to find out which one of the Bell states was sent at the scheme's input. This measurement also referred to as the measurement in the Bell basis. Let's see how it works. So, this is the scheme. Suppose we have a Bell state beta 00 at the input. Beta 00 is actually the state 00 plus 1, 1 over the square root of 2. After the C-node operation, it turns into the following combination. The first state doesn't change, and the second bit, and the second term has the second qubit flip. Again, it is divided by the square root of 2. We can rewrite it in the following form using the fact that these two terms are tensor products. So we have 0 plus 1 divided by the square root of 2 multiplied by 0. And this state, after the Hadamard gate, will turn into the state 0, 0. And thus, the measurement will give us 0, 0. We can also consider in another situation. Now we can have the Bell state beta 01 at the input. Beta 01 is the state 1 divided by square root of 2, 0, 1, plus 1, 0. The C-node elements change it to the following. 1 over the square root of 2, 0, 1, plus 1, 1. They can be rewritten in the following form. 1 over the square root of 2, 0 plus 1, multiplied by 1. And again, after the Hadamard's gate, this state turns into the following: 0, 1. And thus the measurement will give us 0, 1. Continuing in the same way, we can get the same results for any other Bell state at the input. In fact, 2 qubits in a Bell state act as a resource that Alice and Bob can use for the information transfer using the classical and quantum information channels. The information can be transferred not only using the qubits values, but also using the relative phase between them. That is, the phase between the states 0, 0 and 1, 1. In particular, this allows one to transfer 2 classical bits of information using only 1 qubit via the Superdense Coding protocol. So, let there are 2 qubits in a Bell state, the beta 0, 0. The first qubit is being sent to the Alice, and the second qubit is being sent to Bob, as it is depicted on the slide. Suppose Alice wants to transfer the values of 2 classical bits of information. These are 4 such values possible, just like the number of Bell states: 0, 0, 0, 1, 1, 0, and 1, 1. In order to transfer one of these values, Alice must perform the corresponding logical transform on her qubit. If Alice wants to transfer the value of 0, 0, then the transform she needs is just an identity matrix. In other words, she must do nothing with her qubit. If the value she wants to transfer is 0, 1, then Alice has to apply the x logical element to her qubit. She must apply the z element if she wants to transfer 1, 0, and apply the element x and z in turn if she wants to transfer 1, 1. After Alice performs one of these transforms, according to the value she wants to transfer, she sends her qubit to Bob, and he performs the measurement of the qubit pair in the Bell basis. As a result, Bob finds out in which one of the 4 Bell states the entangled qubit pair was after the transforms made by Alice. So, this is the scheme. We have here the Bell state beta 0, 0. The first photon from the EPR pair goes to Alice, and the second one goes to Bob. Here is a table of transforms that Alice should perform on her qubit. And then this qubit is being sent to Bob. Bob performs the Bell measurement and obtains the result. Suppose Alice wants to transfer 1, 1 to Bob. Then she must apply the zx transform to her qubit. Okay, consider this. This is the Bell state. 1, 1, 1, 2, divided by the square root of 2. Then the zx element applied. Zero, 1, 0, 2, plus 1, 1, 1, 2, divided by the square root of 2. Okay, and where will it lead us? This transform will turn this superposition into the following expression. 0 sub 1, 1 sub 2, minus 1 sub 1, 0 sub 2. So it's just a regular rule of how does the zx transform act. Then Bob performed the measurement in the Bell basis And we have already discussed how it is done. Here's the Bell measurement. After the C node or Cx operation, he will have the following: 0 sub 1, 1 sub 2, minus 1 sub 1, 1 sub 2, over the square root of 2. Then, after the Hadamard gate, he will obtain the state 1, 1. We considered this before. And this will lead him to the result 1, 1 after the measurement. This is exactly what Alice wanted to send. So, we have considered the Superdense Coding protocol, which allowed us to transfer two classical bits of information using only one qubit entangled with another qubit. This protocol is quite simple, but it clearly demonstrates how the quantum entanglement being used for practical purposes. We use the Bell state beta 00, but actually any other Bell state could have been used. We note that the Superdense coding does not have any classical analogs. The same holds true for the quantum teleportation, which we consider in our next lesson. That's all for now. Thank you for your attention.